Hello, everyone, and welcome to the show. This is the Geek Nighter podcast. I am your host, Kaival Yapte. Today, I am joined by Soren, who is the founder and CEO of Prisma, which is probably popularly known as a ORM and database tooling solution. But now we also have Prisma Postgres, and that's what probably we are going to talk about in this episode. So, welcome, Soren. I'm really excited to have you today. Let's start with a brief introduction, a little bit about your background, what you're currently doing, and so on.
Thank you, and thank you for having me on the show. I'm really excited for this conversation. Um, so let's start with a big background on Prisma and this journey we've been on. Prisma itself is 8 years old now. We, me and my co-founder, we had spent a lot of time building different startups. We've been in a startup accelerator in London, and we've been through this phase of really rapid iteration, building new products, building small companies. And we always wanted to have a product that was that would facilitate that better. We'd been using backend as a service tools like Firebase, Parse, these kind of things, but we found that we could only really get a small part of the way, and very quickly we had to kind of re-implement the things we were building. So that was the original impetus for what became Prisma. In the beginning, Prisma was not an ORM at all. It was a backend as a service that offered a database and a GraphQL API that was automatically generated to fit that database. And just like the backend as a services we were using before, we ran into this problem that lots of people were excited about it. We got about 100,000 applications deployed on this thing. But we found that the best customers, the ones that were building real things, well, they were building prototypes on our product, and then when they had validated the prototype, they would go and rebuild it with real tools, not with our thing. That was a real problem for us, and that's when we took a step back, made this change, and Prisma became what it is today, an ORM that is now used by I think it's fair to say the majority of application developers who use TypeScript and Node.
Absolutely. I mean, yeah, Prisma is really popular, and I also wanted to understand this journey from let's say being a backend as a service to an ORM layer to a hosted database now, which is also, by the way, congratulations on the GA launch of
Thank you.
Prisma Postgres. So, how did this journey came into picture? Like from an ORM to why did it make sense to create a Postgres database, for example?
So the path to Prisma Postgres, a hosted Postgres offering, is a long one because very early on in our journey, our users started talking to us about the challenges of picking a hosted database, of working with that database from serverless functions, later from edge functions. And that led us down this path of building cloud services that would help with that. And we always resisted doing our own hosted database. We thought there are lots of great database offerings out there. People should just use those and then use Prisma together with them. So about 3 years ago, we launched Accelerate. And Accelerate is this global connection pooling and caching solution that makes it really efficient to query a centralized relational database from either your serverless functions or from edge locations. And that was very successful, but people still come to us and say, why can't I get the database from you as well? Why do I need to work with multiple vendors? I need to have an account with Prisma to get Accelerate, and then I need to go and sign up for some other company to have the hosted database. So we were kind of dragged into this, and eventually we said, okay, it actually does make sense for us to also offer the database hosting. But we didn't just want to host a database and say that's it. We really wanted to have something that was quite different from what is in the market. And that's how we kind of made sense of this. So that's how Prisma Postgres came to be what it is. And I'm excited to kind of dive into some of the details and talk about how Prisma Postgres is quite different from what is in the market today. But that was the
Absolutely.
journey. It was really our user base that in the end convinced us to go and do it.
Yeah, I mean, if it's coming from the users, probably it's the right decision.
Yes, that's one thing I've learned in all those years.
Yeah, that's cool. I mean, now that you explained me this journey, in my mind also it kind of makes sense from the user's perspective. Like people who are already using Prisma, why not just also have the database offering so they kind of get up and running really quickly. You mentioned that, and that's a very key point, that there are so many database offerings, specifically Postgres compatible
Yes.
database, right? And you mentioned we wanted to build something different. So at a high level, if you have to let's say list a few differences with other database offerings, what are they going to be?
So one thing that we have wanted from the beginning, and that is very aligned with the needs of our community, is we want databases to be simple. Traditionally, databases have been and still are these very specialized, fragile things that you have to manage, to babysit. You have the one database and you don't want to overload it or overwhelm it. You have to be really careful. And that's different from pretty much anything else we're doing as software developers these days. We went through the microservices thing. We are treating our applications as cattle, not as pets. Everything can be torn down, brought up again, but the database is different. It's still very fragile. So we really wanted databases to be more like just pages in Notion. Creating another database should be as simple as creating another page in Notion. So that was the core idea. How can we make databases super, super simple? And from there, we went down the Unicraft, Unikernel rabbit hole. We wanted to see how can we make a database perform as well as any other database, but be as lightweight, as cheap as possible, so you can just spin up databases. You don't really have to worry about it.
That's interesting. And the line that you mentioned, or the statement that database, or creating a database should be simple as creating a new page on Notion. And I also read this on your blog, and I would recommend everyone to read the blog because it's quite interesting. It also talks a little bit about the architecture and how things work. It also mentions why unikernels and micro VMs solve the problem of cold starts, and the binary size as well. But we'll get into that details
That's great.
a bit later. But I think let's get started with understanding at a high level, right? So let's say I am a developer. I want to understand, okay, when I transition my workload to Prisma Postgres, I want to understand like how things are, like what are the key components involved in when I say Postgres, Prisma Postgres, and what is the high level architecture like? So how would you describe that?
So Prisma Postgres is really just a standard Postgres database, but then it's hosted in this Firecracker micro VM unikernel setup. But also, Prisma Postgres is a part of the Prisma ecosystem. So if you're used to the Prisma tooling, the Prisma CLI, the Prisma ORM, Prisma Postgres is really easy to use together with that tooling. There is now a command in the Prisma CLI. If you do Prisma init, there's an interactive flow for you to just create a database. Really simple. So if you are in that world, Prisma Postgres just fits in. And we can talk about the components that make that happen. I already mentioned Accelerate. And Accelerate is now a component of Prisma Postgres. It is the routing and ingestion layer to Prisma Postgres. So all queries to a hosted Postgres service, it goes through Accelerate. That means you can connect to it from anywhere. You can connect to it from a normal server, from your local machine, of course, from serverless functions, or from edge locations. And Accelerate is sitting there in the middle, making sure you have the optimal connection. It also means that you can do global caching. No matter where you're querying from, you're able to cache the query results very close to the end user. And the other existing component that is part of Prisma Postgres is Pulse. So Pulse was the second product we launched about 2 years ago. And Pulse is a change data capture solution. That means that it will take the data changes that happen in your database. It will read them out, store them forever. We are storing them on R2 cloud storage. And then you can replay them later. That is great if you have an application that needs to stream in data in the front end, or if you need to process background jobs or something like that. But it's also great if you have a complete database and you want to be able to do point-in-time restore, for example. So that is a second critical component of Prisma Postgres. And the fact that we've been building out those core components over the last 3 years is what enabled us to go and build Prisma Postgres relatively quickly. And because those are critical things that really have to work. But we don't have to build them because we already built them. They are there, and they are now part of Prisma Postgres.
Interesting. So, I mean, you talked about at a high level, let's say 3 components. One is definitely Postgres, but it's, let's say packaged under a unique kernel. And then you have Accelerate, which already existed, which is this global caching and, connection pooling solution. And then you also get change data capture using Pulse. And all 3 things are they different products, or I get it as the same product offering?
With Prisma Postgres, they are part of the same product offering. They are just there, and you can interact with Postgres through the Prisma ORM. So just make normal queries, insert, update data, and you can also subscribe to change events. So the Prisma ORM has an extension that enables you to subscribe to changes from any table. You can even read events that happened in the past. All of that is neatly bundled together.
Okay, very interesting. So, I mean, that's always easy if we just get it as a package. So I don't have to think about, these different things. And most importantly, I don't have to think about setting it up. So that's great in terms of user experience. You mentioned that whatever query you have, using your Prisma application, it goes to Accelerate and then it takes care of the routing. And you also used the term for, globally, you can have your database. So how does this routing work? Like, what does routing in this sense even mean? So, I mean, at a high level, I understand that my query should go to my database. Probably that's what you mean by routing. But how is this mapping working? Where is Accelerate, let's say, deployed? In my case, for example, I'm a software company in Berlin. I use a Prisma application and I want to host my workload on Prisma Postgres. So where is this all happening? Who is setting up the routing? And, let's go through that journey a bit.
So when you have a database, that database lives in one location and you pick that location. Prisma Postgres right now supports 3 different regions, and we'll be adding more regions over time. The Accelerate routing layer has 2 components. One is a component that sits right next to your database. In the case of Prisma Postgres, it will be on the same physical machine as a separate micro VM. But in the case of Accelerate in general, it will be in the same AWS region as your databases. That's the component that makes the query to your database. And often when you have a Prisma query, that will end up resulting in multiple requests to your database. And you want that round trip between where the query happens to your database to be as small as possible. So that means if your application is at the other end of the world, you want to send your Prisma query all the way to your database and then do this little bit of ping pong. So you minimize that latency and then have the result go back to your application. So the second part of Accelerate is that global thing. And that thing is deployed on Cloudflare workers. That means we are in about 400 locations worldwide. No matter where you are, if you're running inside AWS, if you're running on Edge functions, or even from the user's browser, you'll get to the nearest Cloudflare location, which is usually the same city. That's where we'll determine what application you're connecting to, whether you have the right permissions to do the query, and where your database is running. And from there, the query then goes to the database near component that sits like right next to your database where the query happens.
Okay, that's interesting. And so I have to set it up like where I want to, deploy my database. And then based on that, it goes to that particular region. And since you use the Cloudflare workers, you're already globally kind of spread out. And most probably it is going to be, let's say, in the same city as the application is running, and or let's say the same region. And then it will go to the other component of Accelerate, which is running on the same physical hardware, and that then handles the query part, right?
That's correct.
So what is this, the other part of Accelerate, which is running in the same, let's say, this some micro VM? What exactly does it provide? Why was that component required?
It's mostly an artifact of how the Prisma ORM works and has been built historically. So we can take a small detour here and talk about the Prisma ORM and its architecture. When we first made Prisma many years ago, we thought, well, TypeScript is great, and there's this new change with the much more dynamic types that enable us to deliver a really great developer experience. The Prisma API was possible because TypeScript is a very advanced language. But at the time, very few backend applications were written in Node and TypeScript. So we thought, okay, TypeScript is going to be our first language, but eventually we will want to support many different languages. So the core of the Prisma ORM we wrote in Rust, such that could be embedded and used in multiple different languages. Then we have a relatively thin language binding that provides the TypeScript typing. Since then, of course, TypeScript and Node has just grown and grown and grown, and we're now confident that we can build a good business only focusing on Node and TypeScript. But we still have this separation. We have the query engine, which does all of the work. And that's the thing that is placed close to your database in Accelerate. And we get this side benefit of this, that you can construct very complex Prisma queries that don't map neatly to a single SQL query. It requires multiple round trips from your application to the database. And that's not a big problem if you are deploying your application on a long-running server in AWS right next to your RDS instance, because you have single-digit milliseconds between them. That's fine. But that's not actually how most people deploy their applications. Most people deploy their applications certainly in a different availability zone, but maybe in a different region using a different provider. Maybe they're deploying to Vercel or Netlify, and they don't even really know what availability zone they're in. So that's the benefit you get from taking the query engine and putting it right next to your database.
Interesting. So okay, so I think that makes sense. So the client is pretty much lightweight, and the actual query processing and the that main heavy lifting is actually happening on the very close to your database, and
that's right.
That also helps you minimize, of course, the round trip, but also the data that is transferred, right? So you don't have to make a lot of decision outside of the database, but you get all like the final query result right after it leaves your database, right?
Correct.
Okay, that's interesting. Cool. So I think that part is clear. You mentioned you have your Postgres binary, and what were the changes that were required in terms of baking it inside, let's say, a micro VM? What parts were left out? What were the changes made? Is it the regular Postgres binary that I get, or some parts were trimmed off, or was it re-implemented? Let's talk a bit about that part.
So a design goal for us was to have Postgres be as normal as possible. Many other modern database providers, they do these things where they really change how Postgres works. They have a different storage layer, for example. They do special things in Postgres to deal with multi-tenancy. That's a lot of work, and you can go and do that work and deliver a great experience. But it also means that for the end user, it's now no longer normal Postgres. It's this specialized thing. So we wanted to deliver those same benefits, but while keeping Postgres just as normal as possible. So the kind of modifications we have done is stripping out a bunch of stuff that isn't really needed. We've been able to significantly reduce the size of that Postgres binary. But that's the only thing we have done. We have not added any modifications to Postgres. Instead, all of the modifications are around Postgres, how we are instrumenting it, how we are running it in this micro VM setup.
Interesting. You mentioned some of the parts were stripped off. What were those parts, and how did you figure out that those parts are not required?
A lot of it is internationalization, tokens, things like this. Just stuff that you don't really need. And normally, if you have a long-running Postgres server, it's not a problem. Whether that binary is 150 megabytes or 50 megabytes doesn't really matter. When we are running millions of those and starting and stopping them all the time, it does start to matter. So that's why we cared about it. But this is a process that is well documented by Postgres. You can go and do that yourself if you're interested in a smaller binary. If you go and look in the Docker world of Postgres images, there's people are describing how to do this.
Interesting. I'll definitely take a look at that because that sounds interesting to me. Okay, cool. So we talked about the routing layer or the caching layer. We talked about the query engine that lives within, let's say, near to your database, and then the database itself, which is a slim version of the traditional Postgres. And you mentioned a very interesting thing, and I've interviewed or let's say done podcast with few other Postgres solutions where they trying to provide tenant isolation, and they have to re-implement the storage layer to make sure it's fast and it's providing the tenant isolation, and creating a new database is quick and all of that. For example, Neon also has their own implementation of, let's say, an LSM based storage engine and so on. But then you took the other path. You said, let's keep Postgres as it is as much as possible, but then let's make it really small so we can make it really performant. And that's an interesting idea. How did you know that this is the right way to do it, or let's say this is the right path as compared to the writing your own storage layer? And just because you mentioned that for the user we need to give the experience as close as traditional Postgres. But if I think from the user's perspective, they mostly care about the query side of things. For example, what kind of the interface basically.
Yes.
What other features were you able to provide by using Postgres as it is versus writing your own storage engine and stuff like that? And how did you kind of know that this is a better path for us?
So we have the benefit of a very large community that tells us what they want. We have about 1 million developers who use the Prisma ORM every month, and they come and talk to us, right? They talk to us about the competitive landscape, what they like about other products, what they don't like. And one thing we heard again and again is that in general, people really like this modern version of hosted databases, something like what Neon is providing. But they don't like that it's custom, that it's different, that it's a little bit weird. They would like for the database to be just normal Postgres. They want the benefits of the auto-scaling and the scale to zero, the serverless billing model. But they really want it to be as close to what they can run locally, what the ecosystem works with as possible. So that was a hard constraint we set for ourselves in the beginning. What we've also gotten from this is that it's doing what Neon has done, for example, is a lot of work. It's very complicated tech. I kind of think of Neon as an open source version of Aurora, and it's really, really cool. It gives you the ability to do this time travel thing. You can do branching. Super cool. Also really complicated and fundamentally changes what the product is. So we said let's not do any of that. Let's instead have it be normal Postgres, and let's look at standard technologies that we can use to provide the same core benefits that people care about: the auto scaling, the scale to zero, serverless billing model. And then, in order to really hit the price point that we wanted to be at, we made one other decision, and that was let's not be in the normal cloud ecosystem. If you go and look at the price of hardware, the price of compute, it's just gotten phenomenally cheap over the last 10 years. But then you go and look at the price for AWS, the other big cloud providers. And in the early days, they did good price decreases every year, every 6 months. EC2 would get cheaper. For the last 10 years, that hasn't really been the case. AWS doesn't get cheaper anymore, even though hardware keeps getting just phenomenally cheaper. So we are running Prisma Postgres on our own bare metal servers in a traditional data center. And that enables us to tackle the problem with brute force, really. We can just get lots and lots of storage bandwidth, lots of NVMEs in the server, lots of memory. Not a problem. And that means we can go and deliver that same value, creating millions of databases without really worrying about it, simply because our compute infrastructure is so much cheaper.
Very, very interesting. And you mentioned a good point. Like AWS used to be cheaper as compared to, let's say, spinning up your own data center. But
Yes.
now I guess there's a lot of competition, so discounts are a bit rare, and also the price has not that like decreasing as much as the decrease that we see in hardware price. So that's so true. One challenge that I see with this approach, though, is spinning up a new region for your database, specifically for users who have these boundary concerns where, oh, my data should live within the US or within
Yes.
the EU and so on. What are your thoughts on that kind of challenge? Is it still in 2025, it's still challenging, or it's easier than before?
So there are multiple parts of this challenge, right? One is if you're simply deploying into AWS and you can just run on an EC2 instance, then your minimal cost to deploying in your region can be very, very cheap. So we know this because we are already operating Accelerate within AWS. We are in almost all the regions, and the way Accelerate works is we have a warm pool of small EC2 instances, so they're always there and ready. And for us to go into a new region with Accelerate, it costs like $400, something like that. That's the minimum cost. Because we're running on bare metal servers, if we were to do the same in AWS, you need to get the metal instances, which costs $5,000 and up minimum just to get started. So if you want to go and be in all the regions, it's a heavy upfront cost. The same is true for servers that we run ourselves. So you need to go and buy them and put them somewhere. And that's a heavy upfront cost. So that means it is going to take a little bit longer for us to build out these regions. And that's fine. That's just a cost we have to pay. We're going to slow down the rollout a little bit because of this. But because we are so relatively big, we have 1 million developers that are using our ORM every month, we're going to saturate our regions pretty quickly and can then justify building out more regions.
Yeah, interesting. I have one more question here, then we can go back to the technical part again. So again, yeah, spinning up a new data center is definitely challenging, takes time. but also maintaining a data center is a challenge, right? So how did you build, a team who can manage data centers for you, or, what were your thoughts on that?
So it's actually relatively simple for us because we have a single unified service we are running. We are running only one kind of workload, and we're running lots and lots of that workload. So if you are a more traditional company, you have multiple different app servers and databases and this and that, and you need to figure out how to place all of that and your multiple servers in a virtualized environment, maybe. That gets really complicated. For us, it's very simple. We get a big old server, and then we install our software that does all the micro VM stuff. And if one server doesn't work anymore, we just migrate all of those VMs to another server. Any server is like another server. It doesn't really matter. So from that perspective, it has been pretty simple for us, and to some extent, it's simpler than having to deal with Kubernetes and all like Terraform, cloud stuff. That whole world has a bunch of complexity in itself.
Okay, very interesting. Cool. So three components. The accelerator, like the thing that is distributed, then the accelerator which is there living with the database, and then the small Postgres binary itself, and that is deployed on bare metal. It's not on cloud. You have your own data center, so that part is pretty much clear. Where is, so you mentioned that you run within micro VM, and to make these really small binaries spin up really quickly, and you also touch base a little bit on the fault tolerance part of it. But in the blog, there's a mention of cold starts, right? Specifically, if you have an application that is not making any queries, probably it will scale down to 0, and then a query comes and it will take some time, and that may impact your users because they may see higher latencies, which is a real problem that I've also faced. How does micro VMs help in these cases, specifically cold starts, and how do you deal with it? Did you find any specific challenges related to Postgres in that sense?
Postgres is obviously a stateful service, right? When you start a Postgres server, it takes a while for it to start up, and then you start querying it. It starts loading data from the disk, and it builds up its caches. And you really need those caches to be warm in order to have a Postgres server that performs well.
Right.
So you have the startup time, which can be seconds. Then you have the data loading and cache warming, which can also be seconds. So if those are part of your cold start experience, it's not great. There's no way you can deliver a good service. So what we are doing is we have Postgres running inside a micro VM. We're using Firecracker. And then we use Firecracker to take memory snapshots of the Postgres process and store that entire thing to disk. This is actually where the size of Postgres becomes important, because the biggest overhead we have is writing that snapshot to disk and then reading it back from disk into memory. That is what determines how quickly we can perform a cold start. And because we have really minimized the size of the Postgres binary, we are able to do that restore, read the entire memory snapshot from disk, load it into memory, and serve the first request. We can do that in about 5 milliseconds is our average. So that's fast enough that people don't notice that there is a cold start. You don't want to pay that 5 millisecond cost on every single query. But if you haven't used your database for a while and the first query takes an additional 5 milliseconds, that's good enough that you don't even need to worry about cold starts.
Interesting. You mentioned about the snapshot, right? Let's dive a bit more there. Like, what exactly do you mean by snapshot there? And what derives the size of that snapshot? Is it just the Postgres binary size? Is it also the data that was loaded, or what was?
It's the used memory of the Postgres process. So Postgres might claim more memory, but not really use it. That's not part of the snapshot.
Okay.
But the caches that Postgres builds up and uses for query processing, that's part of the snapshot too. And reading those in serial from disk is really, really fast compared to the random access you would have to do when you're building up the cache in the first place.
Okay.
And that's the major benefit. It's just a linear scan of all that data from a fast NVMe disk into memory. We can do that in those 5 milliseconds.
That's really cool. But then and correct me if I'm wrong, but that does depend on my data as well. Like if I have a huge database, or let's say database table, of course, not everything will be in my cache. And you take a snapshot, there's still a possibility that, my query will hit the disk because it won't be there in the cache.
Absolutely.
So is that still fine for the cold start? Or okay, so cold start is mainly that your database is coming up and not the query hitting the disk, right? Okay, so I think I answered my question while I was thinking out loud. So,
but it's a great question, and it points to a trade-off that we are making. Traditionally, when you are configuring hardware and tuning your database server, whether it's Postgres or MySQL or SQL Server, something else, you really want to have your working set in memory. You want your hot data to be in memory. And these database systems, they do a great job of caching all of this data. You certainly want all of your indexes in memory. But maybe you also want some of the tables that sometimes see partial table scans. You want those also to be in memory. And that's because traditionally you have been running these databases with relatively slow disks. So in the old days, it was actual spinning disks, right? But now in the world of cloud, it might be a network attached storage device. It might be EBS on Amazon or something like that. And if you go and look at the IOPS you can get out of those things, it's really slow. You have a small amount of IOPS and you have latency. So you really do not want to be doing multiple random reads from that block device just to serve a single query. You want to serve that from memory. But we're in a different world. We're running your Postgres database on a bare metal server with direct attached NVMe disks and lots of them. So we have really, really, really high bandwidth and very low latency to your disks. And that means it's totally okay if your query, it's totally okay if all of your queries ends up reading from disk. That has the nice benefit that we can reduce the size of those caches, which help with the cold start problem. It also means that you can do table scans. It's okay. Don't do too many of them because you're gonna end up saturating your disk allocation. But if you once in a while have a table scan, you can do that and still have interactive response times in your application.
Yeah, very cool. So it basically ties all back together to the small size of the VM that makes the the size of the snapshot, and then the cold start.
Yes,
it impacts basically everything in a positive way, which is great. Cool. So I think the size of the binary really matters a lot, and then you also mentioned about the data can be of any size. That doesn't really matter a lot, and you take snapshots, and that snapshot itself is relatively smaller. When exactly is this snapshot taken? Is it like periodic, or is it when the VM shuts down?
So we have two different kinds of snapshots. One is the memory snapshot, and that is you should really just think of that as us pausing and resuming the database. That happens in the background. You as an end user, you're not worrying about it. It doesn't impact you in any way, other than the fact that you have these 5 millisecond cold starts from time to time, and the fact that you're not paying for a database that is running when you don't need it. So that's really, think of it as a traditional virtual machine that you pause and resume. Then we have the other kind of snapshot, that is your database backup kind of snapshot. So periodically, we will take your data directory, we'll do a consistent snapshot of that and store it on remote storage on R2. And that is part of our kind of backup disaster recovery mechanism.
Interesting. That's cool. So okay, so you take the snapshot and you talked a bit about the fault tolerance. Let's say the machine dies and you have to move the snapshot that you've taken. Since it's already on disk, you can take it to some other machine and spin it up. And again, since the other machine is also like smaller version running in a micro VM, the cold start isn't a problem. You have this 5 millisecond on average. But then what happens to the in-flight transactions? Are you also moving that state to a new micro VM, or it's a failure, or what happens then?
At the moment, we are not doing that, and I'm not sure we ever will. This scenario only happens when the host, the bare metal server you're running on, has a catastrophic failure. We don't expect this to happen often at all. In fact, we expect a server to run for 5 years without this happening once. So it's a very infrequent event. And when that happens, it's very important that we don't lose your data. But it's probably less important that the 5, 10, however many transactions you have in flight are not interrupted. Instead, what we're doing right now, we abort those and you can retry in your application. And I think that's going to be good enough. So that'll be what we continue to do. Now, there is a different scenario where we will want to move your data, and this will be more frequent, and that is when we need to rebalance our servers. Because right now we are allocating your databases to one of the physical hosts, and what can happen is those databases placed on one host, they can start to get more traffic and it can get unbalanced, right? So we will have to then move one or more of those databases to a different host. And when that happens, you absolutely don't want to be dropping connections. So we have this routing layer I described before that sits in Cloudflare workers. And we haven't built this yet, but what we can very easily do is we can hold connections on that level for a while we do the underlying migration, so that you will see a small slowdown while your data is being migrated. But then your queries will just resume as normal. You don't want that delay to be very long, because now all of a sudden your application will have to deal with this, and you might actually prefer for them to fail so you can respond appropriately. But if it is in the order of a few seconds, I think that can work. So we haven't implemented this yet, but I expect that we will.
Cool. I think that's very interesting. And yeah, I mean, scaling up is probably a more relevant use case for you rather than fault tolerance. I mean, it can also happen, but as you said, it's rare. It's not like cloud environment where it happens pretty often.
Correct.
So you have a bit more control there, and which makes it really good. And then the other good part, which I really like, is the retries or the slowdown itself is also happening behind this accelerate layer, right? And to the user, okay, maybe there are some users who may identify some slowdown, but from the application's perspective, it's still fine. They don't have to implement this retry logic, which is really good. Okay, cool. Let's talk about the other component, Pulse, which you mentioned about change data capture, right? Where exactly that sits? Is it also on the database? And what exactly happens? Where does it take the data to? And from the user's perspective, if I want that data somewhere, I don't know, in Kafka or something, how can that be?
Those are great questions. So what is Pulse? Pulse is this change data capture component. It connects to your database. It presents itself as a read replica. It creates a replication slot. And this is standard functionality in all modern databases. when I started building real-time applications 10, 12 years ago, this was kind of difficult and was very much an internal thing in databases. You had to hack the system a little bit to be able to present yourself as a read replica and get this data. But now it's a very well understood mechanism. There's very robust tooling and a robust ecosystem around this. So Pulse just slots right into that. Just like DBCM or some of these other industry standard systems, Pulse presents itself as a read replica. It creates a standard slot. It gets this data. So what does Pulse then do with the data? Pulse uses a two-tiered storage approach to make sure we can get this data out as quickly as possible and persist it somewhere. So that's the first tier. We're using SQLite in Cloudflare for this first tier. And then we buffer up some data. And when that data has reached a certain size, we write it out to R2, Cloudflare's S3 competitor. And then the data lives there forever. The great thing about change data capture data is that it documents something that happened in the past. It never really changes. So it's just a simple log of everything that has ever happened. Kafka is a perfect mechanism to implement something like this. But we don't like Kafka. We don't like anything that has to run in a cluster and coordinate with the HD or something like that. So that's why we've been building this on Cloudflare workers and using just simple, cheap cloud storage as the final resting place for this data. That means we can store it forever, and you can then go and query that data later from your application if you want to. And we can use this for point-in-time recovery in Prisma Postgres.
Okay, cool. That's really interesting. And one of the pain points that I have seen, at least in my experience, when you have to, let's say, upgrade the database version for Postgres, and I have a couple of questions there. So first, since you have stripped off a lot of things from Postgres, how do you keep the Postgres to its latest version? And the second question is, when you have to upgrade it, I've typically seen that you have to, let's say, delete the replication slot and then take down the connector and do all that stuff as well. And then you have to make sure once you have let's say, new database, the LSN is matching and stuff like that. So the what is that? The change data capture is not broken. So how is that taken care? Who takes care of that? And from the user's perspective, do I have to even worry about it?
So this is the reason Pulse exists as a component that is part of Prisma Postgres, because normally you would have to create a replication slot and connect with something like DBCM, extract the data, store it in Kafka. And that means you as a developer, or maybe your system administrator, somebody on your team, is responsible for all of this stuff. But with Prisma Postgres, it's part of a complete package. So that means if we go and upgrade the database, well, we know about all of those things. So we have automated systems that take care of all of it. You don't really need to worry. All you need to worry about as an application developer is the data you put in the database, the data that is in the database, and then the events that you can get out of the database through Pulse. You don't need to worry about the internals, because Prisma Postgres manages the two sides of that to make sure it always stays in sync.
Okay, interesting. So basically, Pulse takes care of that, and user even doesn't have to worry about Postgres versions, and all these maintenance activities are taken care by a hosted database solution anyway. So
yes,
it's good. Cool. And sorry, I'm not sure if you answered the first question, which was about how do you keep the Postgres version compatible with the latest one?
So that's a great question, and there is a bit of manual work from our side for every new version of Postgres that we want to deploy. We launched Prisma Postgres just a few weeks ago, so we were able to get on the latest version, Postgres 7. That's really nice. And we will be automatically rolling out minor updates. But then when it comes to major versions of Postgres, I expect that will be a user-initiated action. It will be fully automated, but there will be a way for you to log into the Prisma Postgres UI and click a button. And we are not just automatically taking the latest versions and rolling them into the system. There is a little bit of manual work we're doing to strip down the size of the image to make sure everything works. And when we've done that work, we'll make it available in the system.
Cool. I mean, one of the powerful aspect of using Postgres is it's the extension ecosystem, right? And
yes,
what happens? So in one place we have stripped down the database to minimal size, but then if I have to extend it using some extensions, just I don't know. Nowadays Postgres has like PG Vector and PG DuckDB and search and analytics. Like everything is just
Postgres can do
one.
everything.
Everything, yeah.
That's
just
why
use
Postgres is such a
exactly.
powerful ecosystem, right? Because it has all of these plugins. No matter what you want to do, you can do it in Postgres as long as you install the right plugin.
Right. So how does that impact the size of the binary though?
It does impact, and if you install all of the popular extensions, you more than double the size of the Postgres binary, and that means you more than double the cold start time. Right now, Prisma Postgres has been out for 3 weeks. We don't support manually loading extensions. So Postgres ships with a few default extensions. Those are there and enabled. But what we will do is have a way for you as a developer to decide what extensions you want to enable. And then that's a trade-off for you. If you need PG Vector, well, that half a millisecond extra cold start time is probably worth it for you. So you just go and enable it.
Yeah. Interesting. So again, it's a trade-off that I'm not sure how you're going to expose that trade-off. Like, how do I, as a user, decide? Or, how will you estimate that, okay, if I have like, I don't know, 3 extensions, how much it does impact your cold start and so on. But it's really interesting. It's an interesting problem. Cool.
And we don't know exactly how we will expose this yet, but it's going to be relatively minimal. We are talking a few milliseconds at most.
Okay, really cool. One thing that you mentioned specifically about while talking about Pulse is that you use SQLite there.
Yes.
Why SQLite? Like, do you need some sort of SQL queries there, or what was the reason SQLite was used?
It's mostly an artifact of where we have implemented this system. So we try to build all of our stateful services in Cloudflare Workers. Cloudflare Workers has this wonderful primitive called durable objects, and durable objects solves the coordination problem. Durable objects enables you to create a named entity, and the guarantee that you get from Cloudflare is that there will always, ever, only be one version of that named entity running. And that named entity has local storage. They implement all of this by running Cockroach under the hood in 5 different locations. So they are fault tolerant, but you don't need to worry about the intricacies of that underlying database thing. You don't need to worry about a leader election or anything like that, like you would if you were setting up your own Kafka cluster or something.
Right.
You just worry about your application logic that runs on Cloudflare Worker and has access to local storage. If there's a failure, you'll be moved to one of the other locations. It'll continue to work. In that world, what we have access to is a local SQLite, and that's why we're using that as the buffer space in tier 1 storage. We really do not need anything sophisticated. We just need to be able to write bytes to disk up to a certain size, make sure they don't disappear, and then write them out to R2.
Okay, interesting. Fair enough. Cool. Let's talk a bit about users who are currently using some Postgres database, I don't know, some other managed service or just vanilla Postgres deployed on cloud, um, what is the motivation to move to Prisma Postgres? I mean, of course, one biggest motivation is if you're already using Prisma, it does make a lot of sense. The other
Yes.
motivation could be, I don't know, cold starts, things like that. What are some other points that you would like to highlight?
So if you need a no-nonsense database that just works, Prisma Postgres is a really great choice. The pricing model is extremely simple. You make one query and you pay a very small amount of money for that one query. You don't need to calculate compute hours or anything like that. You don't need to pay a fixed monthly fee to have a database running. You just pay for the queries that your application is making. And that means if you are working on multiple applications, or if you have a side project, but you're not really sure where it's going to go, but you want to make sure that it works in case you end up on Hacker News or something like that, this is a great model because you can have that running on serious production grade infrastructure and pay nothing until the day that you do end up on Hacker News, and then you start paying. That's the kind of the value proposition that we set out to create with Prisma Postgres. What we have also learned from talking to lots and lots of people over the last few months is that Prisma has built a brand that extends far beyond the existing ORM user base. So we've had a cloud product for almost 5 years now, and for the longest time we couldn't figure out why our activation rate on this cloud product was so low. Then we started talking to people, and what we learned is that more than half of the people signing up to our cloud product, they've never used Prisma. They're in a situation where they want a hosted database. They know that Prisma is the database company, so they just go to the Prisma website, sign up for our cloud product, and then get really confused because there is no hosted database. So how can Prisma be the database company when they don't have a database? So we have seen just tremendous uptake in the first few weeks of Prisma Postgres because we've had these people already come in and looking for the database. Where is it? Where is it? Well, now it's there. So those are the two big things, I think.
Awesome. Where can people learn more about it? Of course, they can, look at the website. Probably there are some bunch of resources. I'll also link the blog about Prisma Postgres, its architecture. But where more, like how can people reach out if they have questions or if they're just interested in trying out Prisma or contributing? I don't know.
So Prisma is a huge and very welcoming community. So if you aren't a Prisma user already, we have a Discord server you can go and join and talk to people. We have a support staff that is lurking in Discord. You'll find us online. If you just go on Twitter and talk about Prisma, chances are we'll be there. You can go and find me, send me a DM if you would like to chat to me directly. And how do you get started? Well, there are really two ways. One, you go to prisma.io. That'll just guide you right through it. If you just want to jump right in, you can use the Prisma CLI, so npx Prisma init. That will set up a local project for you and ask if you want to have a hosted database, and then you'll just authenticate with Google or GitHub or something like that, and you will have your local project set up to connect to your hosted database in like 20 seconds.
Awesome. Cool. Well, thanks a lot, Søren, for joining me today and sharing all the amazing insights about the architecture, about the database, about the ecosystem. And it's really, really unique approach that you have taken. And I'm really curious to understand more how things are working. And, if there are any blog posts or any white papers, anything that you would suggest, please share it with me so I can link it in the description. So our viewers can also learn more about, the space. But yeah, thanks a lot. I loved it.
Thank you so much. This has been really fun. I'm going to send over a few white papers. We have the blog post you mentioned. We also have a really nice video just talking through how it works. I'll send over all of that material and you can attach it. Maybe we can talk again in a year and we can kind of see how far we've gotten, how many of those regions we've been able to deploy, so on.
Absolutely.